This is the first problem of this chapter, and the problem is if we have two concentric spherical shells of radius A and B, we have, I have shown here, this is a one spherical shell with radius A, and this is another shell with the radius B, and separated by a weakly conducting material of conductivity sigma. Here there is some material, and these two concentric spheres are separated by some material having conductivity sigma. If they are maintained at potential V, what current flows from one to the other? If there is a potential, some potential difference V, then what current will flow from this sphere to this sphere? It means that in this problem, we have to find out the current I. This is now clear. We need to find out the current I. The question is how to start, and how to start and try to calculate the current. Then we have a relation with current which is equal to J dot dA. Charge, this is equal to J, current density, current per unit area. Then the current we can write down integral of J dot dA. From this equation, it is clear that we need to find out J, and where J is equal to sigma E from the Ohm's law. And if we put this, then sigma is constant and E dot dA. Now to look this equation, we need to calculate the electric field. We will try to calculate the electric field first. And how it is possible? We need to calculate this region. We need to calculate this. And this is nothing but this is the Gauss's law. E dot dA for the closed surface, and this is equal to charge enclosed divided by epsilon naught. So first, if I remove this, then because we know that what we need from is E dot dA. This is for a closed surface which is equal to charge enclosed divided by epsilon naught. And if we find out the electric field from this, then what is the requirement? The requirement is that we have some Gaussian surface, this is a Gaussian loop with some radius r. Then E dA, which is equal to current enclosed divided by epsilon naught. If the current enclosed is equal to Q. And what is the area? What is the area of this Gaussian loop? This is actually 4 pi and r square because the radius is r and the charge is Q and epsilon naught. It means that E, which is equal to 1 over 4 pi epsilon naught r square and charge. This is the electric field, and we have also find out the potential between these two, the potential difference between these two spherical shell. Now the potential difference, how we can relate the potential difference with the electric field, and we know that V, which is equal to VA minus VB, which is equal to minus integral from B to A, from B to A, and this is actually equal to E dot dr. We know about electric field, we have already find out. Then putting the value of E from B to A, and E Q divided by 4 pi epsilon naught r square. From here, minus Q is constant, 4 pi epsilon naught is constant, and only we have B to A 1 over r square, and 1 over r square minus 2 dr. And this actually is equal to, we should write down this I, which is equal to sigma and E dot dA. This equation we have already, because we should putting the value and then we can find out the electric current. So I want to remove this. And from here, the potential is, if we integrate this, then the potential must be equal to minus Q divided by 4 pi epsilon naught, and the integration is minus 1 over r and from B to A. And if I limits here, and after some calculation you can find out the potential, which is equal to this one. So the potential is Q divided by 4 pi epsilon naught 1 over A minus 1 over B. This is the potential, and from this equation the current is equal to sigma into integral E dot dA, and from this equation if I write down sigma, and this is equal to the actually, and the left side and the right hand side the charge enclosed and epsilon naught. Now I, which is equal to sigma Q divided by epsilon naught, this is the final expression, and we need the current, but we know sigma epsilon naught is okay, but here Q is unknown. Q, what is the charge, and how we can relate this to the potential, and how we can find out? Then we need to find out Q from this potential. F from this potential, this we can find out the charge, which is equal to 4 pi epsilon naught V, and this is will be n division 1 over A minus 1 over B. This is the charge, and now putting the value of this charge in this equation, let's say this is equation number 1, putting the value of Q and equation 1. Then we have the current sigma divided by epsilon naught and the value of Q 4 pi epsilon naught V divided by 1 over A minus 1 over B. And this is the final. Uh, we can also have some epsilon naught and epsilon naught. It will cancel out, and we have the current which is equal to 4 pi sigma V divided by 1 over A minus 1 over B. And this is the final current, because in the question we have given that V as the potential, sigma is the charge density, and A and B are the radii of these two spherical shells. And the B part of this problem 7.1 is what is the resistance between the shells. These are the two shells, and we have to find out the resistance between these two shells. How is it possible? We know that from the Ohm's law, V is equal to I and R, and R which is equal to V divided by I. And here we know about the current I. In the previous A part, we have calculated the value of uh, current I, and it was, if I remember, the current that previously we have calculated, it was 4 pi sigma V and 1 over A minus 1 over B. Putting the value of current here, then R, which is equal to V divided by 4 pi epsilon naught no sigma V and divided by 1 over A minus 1 over B. V and V will cancel out, and the resistance will be equal to, this will go to numerator 1 over A minus 1 over B and divided by 4 pi and sigma. So this is the resistance between these two shells. Okay, this is the C part of problem 7.1, and here the statement is, notice that if B is very greater than A, B, the radius, is very greater than A, the outer radius B is irrelevant. The outer radius is very greater than A, then this outer radius is irrelevant. And how do you account for that? Exploit this observation to determine the current flowing between two metal spheres, each of radius A, immersed deep in the sea and held quite far apart. If the potential difference between them is V, the condition is B is very greater than A, it means that 1 over B, this will goes to 0. This is very greater than A. And then the resistance is, we find out at B, Previously, we have calculated 1 over A minus 1 over B, and it is also 1 over 4, 4 pi and sigma. From this 1 over B is actually irrelevant, and this is equal to 0, then the resistance will be equal to 1 over 4 pi sigma and A. So this will be the resistance as if B is very greater than A. The resistance for a single sphere. This is the resistance for a single sphere, because B is very large. So this is the resistance for a single sphere. Okay, this is the radius when B is very larger than A. Now if we have two spheres, this and this, and they are two spheres, then it has the same radius. Then for these two spheres, we can write down the R, which is equal to 1 over 4 pi sigma A plus 1 over 4 pi sigma A, and this R will be equal to 2 divided by 4 pi sigma A. This will be the radius, and we now interested to find out the current. Then current is equal to potential divided by resistance, and this will be equal to 2 divided by 4 pi sigma A, and I will be equal to 4 pi uh, sigma A V divided by 2. 2 will cancel with this, and finally the current around these two spheres will be this one. This is problem number 7.2, and it states that a capacitor C has been charged up to a potential V naught at time t is equal to 0. This is a capacitor, and it has been charged with potential V naught when at time t is equal to 0. It is connected to a resistance R and begins to discharge. Here, this capacitor is connected to a resistor R, then this begins to discharge, uh, and here we are asked to determine the charge on the capacitor as a function of time. We need to find out the charge as a function of time, and then what is the current and the resistance R, and what is the current with changing with time. So we need to find out the expression where the charge is a function of time and the current is also as a function of time. It means that how the charges changes with time and how the current changes with time. So we need to find out these two expressions. How to start to solve this problem, because we need to Q of t and I of t, and we have only the capacitor and the resistors R. Then we should looking for the Kirchhoff voltage law, where it states that the voltage around a closed loop will be equal to 0. And here, what is the voltage here? What is the voltage here? And we need to write down. It means that Vc is the voltage of this capacitor plus VR is the voltage, and this resistor R, and this is equal to 0. And we also know the voltage in the capacitor Q divided by C plus V is equal to I R, and which is equal to 0. And we also know that the current I, where the current I is equal to rate of change of charge. So I is equal to dq divided by dt. It means that q divided by c plus dq divided by dt r, which is equal to 0. Further, if we need to find out q, we move this term to the right hand side, and let I want to remove this to, okay, this q divided by c, which is equal to minus dq divided by dt and r. We need to find q, then q will be at one side and the other terms will be on the right hand side. Q divided by dq, which is equal to minus cr divided by dt, down dq divided by q, which is equal to minus 1 over cr and dt. And then if we integrate this from both sides, then integrate this and integrate this, because these c and r are constant and we are looking only for this. Okay, what is the integration of this? Natural log of q, which is equal to minus 1 over cr t plus log of a. This is the constant of integration, and we must write down this. Okay, uh, I want to write down log of q minus log of a, which is equal to minus t divided by cr, and this is equal to q divided by a by the rule of log minus t divided by cr. And further, if we remove the log from this side, then this will goes to the exponential, and let q divided by a, which is equal to exponential of t divided by cr, and where t, which is a function of time, is equal to a e to the power minus t divided by cr. Now we are looking for this a, the constant of integration. We need to use the initial condition. The initial condition is at time t is equal to 0, the charge is equal to q naught. This is the condition because initially the charge on this capacitor is q, and when this is connected with r, then this begins to discharge. So initially the charge on this capacitor is q at time t is equal to 0. And then we have this relation, if q is equal to q, which is equal to q, then this a and e to the power 0. It means that q, which is equal to a, and here this is a is nothing but this is q. So from this equation, q which is equal to q and e to power minus t divided by cr, and this is nothing but this expression tells us this charge is a function of t. So this is equal to q of t, which is equal to q e to power minus t divided by cr. Further, we need to find out the current. If we need to find out the current, then taking the derivative of this expression, then dq divided by dt, which is equal to q and derivative of this minus 1 over cr and e to power minus t divided by cr. And this is nothing but this is the current, which is equal to minus q divided by cr and e to power minus t divided by cr. I is equal to q divided by cr and e to power minus t divided by cr. And this is the expression of the current I, which is a function of time t. And q divided by r, if I write down, I want to remove this. V is equal to q divided by c. If the potential is V naught, then q, which is equal to c V naught. If we put here, then this current of t, which is equal to c V naught divided by cr and e to power minus t divided by RCR, that remains the same thing, and this I of t, which is equal to V naught divided by R and e to power minus t divided by CR. And this is the current, which is a function of time t. Again, we are asked to determine the q of t and I of t, the same thing, but the diagram is little bit different. Here the voltage is applied and this charge, this is a capacitor which can be charged due to this V naught, the potential, and this is the resistors R. Then how to write down, how to find out q of t and I of t, the expressions, and we need to use the Kirchhoff's voltage law again, because this potential is equal to the potential of this and the potential of this. So solution is using the Kirchhoff voltage law, and according to this, V naught, the potential of this, which is equal to the potential of the capacitor plus potential of the this resistors R, and V naught, which is equal to V Q divided by C plus V is equal to I R. We know about this. I, which is equal to dq divided by dt and R. And further, if I write down this like q divided by c plus dq divided by dtr, which is equal to V naught, and multiply this by c, then what will we have? Cr, which is equal to V naught and c. And further, this dq divided by dtcr will be equal to dq divided by dt cr, which is equal to v naught c minus q. And if I write down dq divided by dt cr, which is equal to minus, then this will be equal to q minus v naught c. And further, to solve this equation, I I want to dq at one side and time at the other side, then dq divided by q minus v naught c. This is equal to minus 1 over cr and dt. And now integrate this both sides from 0 to charge this, and this is integration 0 to t. The integration of this is actually log of uh, q minus v naught c from 0 to q, which is equal to minus 1 over cr and time 0 to t. And putting the value initially for q is equal to q, then natural log of q minus v naught c minus putting the value of q is equal to 0, then this is equal to minus v naught c, which is equal to minus 1 over cr and time t. And further, we can write down minus v naught c divided by minus v naught c, and which is equal to minus 1 over cr and time t. Further, some calculation, if we log of q divided by, if we apply this to separately to q, this minus v naught c minus v naught c divided by minus v naught c. This is equal to minus t divided by cr. Then if we look, this minus minus cancel out, and log of 1 minus q divided by v naught c, this is actually equal to minus t divided by cr. We have this relation. And further, if we remove the log, then this term will goes to exponential. 1 minus q divided by v naught c will be equal to minus t divided by cr. And we need then finally q divided by v naught c, this will be equal to 1 minus e to the power minus t divided by cr, and q of t, this is equal to v naught c 1 minus e to the power minus t divided by cr. So this is the charge which varies with time. And what is the current I of t? So we should differentiate I of t, which is equal to dq divided by dt. And after differentiation, if we do some differentiation, then the current v naught divided by r, v naught divided by r, and exponential of t divided by cr. Check this by yourself. Number 7.3, and the statement is two metal objects. We have two metal objects 1 and 2 are embedded in a weakly conducting material of conductivity sigma. This has been placed in a weakly conducting material which has conductivity sigma. Show that the resistance between them is related to the capacitance of the arrangement by. This looks like the capacitor. If solution of this equation is, we need to find out the resistance R. And if the resistance R we will have V divided by I. The first point is we need to calculate the current I, and we also need to have the voltage V. Then we can show this resistance R. Now we need for the current I, because from this equation 1 we need the potential, we need I. How to calculate I? Then we have a relation between I and current density, which is J dot dA. We know about this. And we also know about J. And J is nothing but this is equal to sigma E, where J from the Ohm's law, sigma E, because we have a sigma. And then we can say that if we put the value of this will be equal to sigma and E dot dA. And what is E dot dA from Gauss's law? This is nothing but Q enclosed divided by epsilon naught. Then I, which is equal to sigma Q enclosed divided by epsilon naught. And what is Q enclosed? What is charge between these two bodies 1 and 2? This looks like a capacitor. Then what will be the charge between two plates? The charge between two plates is equal to CV. Then Q is equal to CV. C is the capacitance. We know the capacitance C, and V is the voltage. Then this Q enclosed is nothing but Q is equal to CV. Then I, which is equal to sigma CV divided by epsilon naught. Putting the value of I in equation number first. Putting the value of I in equation first. Then this R will be equal to V divided by sigma CV divided by epsilon naught. This V can be cancelled with this, and we have R, which is equal to epsilon naught divided by sigma C. So this is the required result. This is the second part of this problem 7.3, and it states that suppose you connected a battery between 1 and 2. If you connect a battery between 1 and 2 and charge them up to a potential difference V naught, if you charge the capacitor, this just like a capacitor 1 and 2 with a potential V naught, if you then disconnect the battery, the charge will gradually leak off. Show that V of t, which is equal to V naught e to the power minus t divided by tau, and find constant tau in terms of epsilon naught and sigma. The question is, we need to find out this expression V of t, which is equal to this. How to start this equation? The main point is this: how we can start this equation. Then we know about the current, because this current is decreases, when this leak of this current it decreases, this will we have a minus sign, I is equal to dq divided by dt. And what is q? What is q between this? Q is equal to cv, and v is equal to ir. If we have some resistance R in the battery, then Q is equal to CIR. From this equation, we can find out the current as well. We have the current which is equal to Q divided by CR. And putting the value here, then this Q divided by CR, which is equal to minus dQ divided by dt. And further, dQ divided by dt, which is equal to minus Q divided by CR. And now, how to solve this further? We have dQ at one side and minus 1 over CR dt. We can write down like this, and then integrate on both sides, natural log of Q, which is equal to minus T divided by CR plus log of some constant of integration. And we also need to find out this constant of integration at time t is equal to 0. We have time t is equal to 0, this log of q, which is equal to log of a. And initially, this is initial charge of this 1 and 2 is equal to q naught, then this is equal to this. And putting the value log of q, which is equal to minus t divided by cr plus log of q naught, and then log of q minus log of q naught, which is equal to minus t divided by cr. And further, log of q divided by q naught, which is equal to minus t divided with this straightforward mathematics, and q divided by q naught, which is equal to exponential of t divided by cr, and q, which is equal to q naught e to the power minus t divided by cr. And we need to find the expression for the voltage. Then how we can relate, because V is equal to Q divided by C, then we can say that this Q divided by C, this is actually if we find out Q, then Q is equal to VC, then this is equal to VC, and this is V naught C e to the power minus t divided by CR, and CC cancel out, then V of t, which is equal to V naught e to the power minus t divided by CR. So this is the required expression, but CR they have written like this: V naught e to the power minus t divided by tau. And we are also asked from the equation that tau is equal to RCR. And what is R from the previous case? From A, R from the previous case, epsilon r divided by sigma, and also C. We know about this. And this tau, which is equal to C epsilon r divided by sigma c. This is from A. Then this c will cancel with this. Then this tau, which is equal to epsilon r divided by sigma, and we are